Hey everybody, welcome to Bill Sky the Assembly Guy. Another video on assembler language. We're going to do both ARM and x86-64. And before you ask, why am I wearing the baseball cap? Well, first of all, I love wearing baseball caps. Second of all, I'm having a bad hair day. I cleaned up and everything. It's just a bad hair day. It has nothing to do with the fact that I'm losing hair. Well, okay, maybe it does. But just deal with it. It's a nice Mickey Mouse baseball cap. We love Disney World, we love Disneyland, and just that's what I'm going to be doing today. So let's get to it. Extended addition and subtraction, doing larger math than you might have thought was possible based on the number of bits that your CPU. So what does this all mean? What does extended addition and subtraction, what does extended arithmetic mean? When you have data which won't fit into a register in the CPU, you can use extended arithmetic to make that happen. This means that you put one half of your number in one register, the other half in another register, and then using the carry flag, you can distribute the math between those two registers. So you effectively are creating one larger register. So let's take a look at this type of operation for x86-64 Intel AMD processors. So some numbers in science, why do we need to worry about this? 64-bit registers are huge. And if you're on 32-bit, well, you don't have as much space, so you might need to extend into multiple 32-bit registers. But most modern applications are written in 64-bit, I should say new applications. So why do we still need this? Why is this still an issue? Well, like it's shown here, some numbers in science can be very large. The number of protons in the universe, the number of subatomic particles in the human body. It's crazy. The number of atoms in the human body is like 10 to the 27th power atoms is the current estimate. So just huge numbers. And those numbers will not fit in a 64-bit register, especially if you say, I want to get all of the atoms. I actually did the calculations last night preparing for this. If you want to do all of the atoms and all of the humans on the planet Earth, for some reason you're given that job, it just won't fit in 64 bits. So what you do is, instead of just using RAX, you use the combination of RDX and RAX together. Now, you don't have to use the combination of RDX and RAX. You can use RBX and RCX. But RAX and RDX are kind of an industry standard, because in multiplication and division, you're forced to use those registers. So it's really a good idea to just stick with that. And so combining these two registers, RDX and RAX, you have 128 bits. That means your largest number is 2 to the 128th minus 1. Very large number. So we can distribute this load, or we can handle the load of these huge numbers inside of those two registers. So let's look at the procedure. So up above, I have this absolutely huge number. It's actually not as big as it could be because I don't have all of the nibbles filled up. But you can see it's zeros, one FF, and then all Fs at the end. Now the 0x means hexadecimal. Normally you have an H at the end, but for mathematical purposes, we put 0x in front. So what you do is you take the first half, the first 8 bytes, and you put that into RDX. So that's what I like to call the upper half. And then you put the lower half, which in this case is 8 bytes of all Fs, you put that into RAX. So RDX and RAX are now sharing that big, huge number. And then let's say we want to add the number 100, all of those zeros and 1. We're looking at the bottom half now of this diagram. You split those up. You move the top 8 bytes into RBX in this example, and I call that upper half number 2. And then you move the bottom 8 bytes into the lower half number 2, which I've decided to make RCX. And the procedure you can see is there on the left, steps 1 through 4. Now, once you do that, how do you do it? Well, what you do is you add the two bottom halves. So you add RAX, which is the bottom half of our original number, you add that with RCX, and then because that will overflow, all Fs with a 1, that will actually carry. We'll lose a bit. The result of RAX will be all zeros, but then you'll get a 1 in the carry flag. And that's where the add carry instruction comes out. So then what we do is we add carry the top half. We add RBX to RDX plus the value in the carry flag, because that was from that extended addition or overflowed instruction or overflowed result from the lower half addition. So that adds RDX or RBX to RDX, and then the 1 from the carry. And so we get that larger number, 300. The resulting number is now held in RDX and RAX. And as I said earlier, that's pretty much an industry standard for multiplication and division. So we're going to stick with that in these lectures. And you can see now the much larger number, 300, and then all the zeros behind it, the 8 bytes of additional zeros, is a much larger number. Now, let's go ahead and subtract. Now, we're going to do this in a demonstration code so you can follow along. Let's go ahead and subtract 1 from this RDX, RAX extended combination. So what we're going to do is we're going to subtract 1 from the lower half first. You always start at the lower half first. So we're going to subtract 1 from the lower half. And what that's going to do is that's going to borrow a bit from just the ether, and it's going to put that in the carry flag. So if you notice, if you subtract 1 from all zeros, you get all Fs. And that's going to put a 1 in the carry flag. And you use the sub RAX comma 1. Or that could be a variable, a byte variable, or actually a double or quad word variable, or register. Now the next step is to subtract the carry flag from that upper half. So RDX is the upper half. So we do the SBB, that's subtract with borrow. We subtract with borrow RDX, and we have the 0H there because we don't want to subtract any additional number. We just want to subtract the carry flag. So you just make that H. So subtract with borrow from RDX 0H plus subtract the carry flag from that, and it goes from 300 to 2FF. And then our resulting number is shared in RDX and RAX. So the 2FF is in RDX, the all Fs is in RAX. And yes, the programmer needs to keep track of these registers for this extended operation. That's why comments are so important in your program. That's why designing the program on paper or on your tablet, writing or notes-taking app is very, very common to do. You want to keep track of this stuff. That's why I'm showing this presentation before doing the demo, simply because I needed to keep it straight in my head. Okay, whew, with all of that done, let's now do a coding demonstration, a debugging demonstration on this Intel AMD x86-64. We're going to do it in 64 bits. So let's get to that demonstration. I hope you follow along. I'm going to use Linux, but you can use Windows if you'd like. This is not going to be ARM. This is going to be the x86-64. So let's get to that demo. All right, x86-64 64-bit demo. Let's get to it. I'm on Linux. Again, you can do this on Windows if you'd like. So I'm going to go into my ASM projects, and what I'm going to do is I'm going to pick the 64-bit functions template. I'm going to rename it 64-bit extended math. Linux. I always like to give them a really nice name. All right. And let's go ahead and do this coding. Now, I'm going to do exactly what I did in the presentation. It's not going to be anything different. It's going to be the exact same thing. So follow along. It's what I presented just a little while ago. And let's get to it. So what I'm going to do is I'm going to move into the upper half. I'm going to move into the upper half of my big number, and that was the RDX register. I'm going to put 1FF. Now I could put all of the zeros in front of there, like I had in the presentation. 1, 2, 3, 4, 5, 6, 7, 8. So I could do that, and to be consistent with the presentation, let's just go ahead and do that. So that's the upper half, and I'm going to put a comment there. And then in the bottom half, which is going to be RAX, I'm going to put 1, 2, 3, 4, 5, 6, 7, 8. Now, why did I put the 0 up in front? Because if the first nibble of a hexadecimal number is a letter, you must precede it by a 0. You know, you could add a space there just to make you feel a little bit better. Okay, and this is our lower half of our extended number 1. Now let's go ahead and do the bottom half. Remember, we were going to add RDX, RAX. We're going to add 2 RDX, RAX, RBX, RCX. So let's move into RBX. And I believe we put 2, 3, 4, 5, 6, 7, 8. So this is the upper half of our extended 2. And we moved into RCX. 1, 2, 3, 4, 5, 6, 7. Oh, I think we need some more. Well, we don't actually need more zeros. But just to stay consistent, let's go ahead and put a couple more in. Again, you don't have to put preceding zeros. I'm doing it just to make them look consistent. So this is our lower half of our extended number 2. And extended number 2 is going to be RBX, RCX. And this register with a colon in between is a very common way of representing these. So this is going to be RDX, RAX. Now, as you're writing your code, I promise you, if you comment things like this, you're going to be looking up at your code for documentation purposes. Okay, so the next thing we want to do is we're going to do step number 5 in our procedure. And I'm actually looking at the presentation while I'm doing this. So I'm going to add to RAX the RCX. I'm going to add the lower half, or I'm going to add the lower half of extended number 2 to the lower half of extended number 1. Remember, you do the lower half first. And what this is going to do, I'm going to add the lower half number 2 to lower half number 1, setting the carry flag. I put in those comments in there. All right, so that was step number 5. Step number 6 is going to be to do the add carry. So I'm going to say add carry, RDX, RBX. So that's going to add the upper half number 2 to the upper half number 1, including the carry flag. And that's it. That is our addition. Now, just so we don't have to debug this multiple times, let's save and build this to make sure I did everything right. All right, looks good. Let's add that subtraction. In the presentation, I also had a subtraction. So let's subtract 1 from this combination of RDX, RAX. So I'm going to subtract from RAX, the lower, you always subtract and add from the lower first. Subtract from the lower 1. Subtract from the lower half 1. And what that's going to do is that's going to turn on the carry flag, because the lower half is going to have all zeros in it, which you'll see in our debugging example. It's going to have all zeros in it. We subtract 1 from it. It's going to turn it into an all Fs, and it's going to turn on the carry flag. So then the next thing we want to do is we want to subtract with a borrow from the upper half, and we're just going to say 0. So we just want to subtract the carry flag. We could put a number in here if we wanted to subtract more than just, the 1 from the lower half, but we're only subtracting 1, so we're just going to leave that as a 0. So this will be subtract from the upper half 0 and 1 from the carry flag. And let's go ahead and build that, and now let's debug it. Use our KDBG, and let's take a look at our code. All right, so let's put a breakpoint right there on our move, and let's run it. And I'm clicking on the Register tab, and let's watch our registers. So we're going to put into RDX 1FF. You can see it down there in red. We're going to put into RAX all Fs. Let's expand this a little bit. Okay, we're going to put the number we want to add to RDX RAX. We're going to put that, the upper half, into RBX. You can see the 100. And we're going to put into RCX the lower half, which is going to be 1H. Now, the debugger doesn't show all the preceding zeros, so you just have to kind of use your imagination a little bit. Now let's add the two lower halves. Let's add RCX to RAX. And you can see RAX turned to 0 because the upper half, or the lower half 1, added 1 to all those F's, which zeroed it out. It also turned on the carry flag. Now we're going to add carry, RBX, the upper half, the number that we're going to add to the upper half RBX, we're going to add that to RDX, including the carry flag, and now it's 300. So our number ends up being 300 and then 8 bytes of zeros, just like the presentation showed. All right, now let's do the subtraction. Now we're going to subtract 1 from RAX. That's going to turn on the carry flag because 1 from 0 is all F's and the carry flag is turned on. So you can see RAX now has all the F's turned on. I can actually scroll down here and look at the E flags. Now you'd have to know exactly where the carry flag is, but KDBG shows it as in red numbers. On Visual Studio, you would actually see the carry flag is equal to 1. So that puts all F's. Now we're going to do subtract borrow. Watch this guy right here, 300. That turns into 2FF. So now our total will, or our combined extended addition and subtraction will now be 2FF and then 8 bytes of nothing but F's. So that is the demonstration for Intel x86-64 extended addition and subtraction. Okay, so that was our coding demonstration. I recommend that you go through the video and you take a look at what I did, and then in your programming environment, go ahead and replicate what I did, go ahead and do it yourself, try it out, and then look at the video solution that I've got as well as to how I did it. Get used to this, try some different numbers in there, see what they do. Practice, practice, practice. It's up to you to become an expert. I'm just trying to get you started. Hope to see you at my next video.